Ladies and gentlemen, I would like to welcome you in this very interesting lecture on robotic learning by Professor Jan Peters from the Technical University of Darmstadt. He is a very well-known scientist on robotics and machine learning. So at the confluence of these two events, before we start, I would like to tell you that in September, AI for Media, Elise, and AIDA organized the so-called 2022 AI Methodology Symposium. This is actually a futurology symposium. So if you have interesting topics to discuss, you can send me an email message and we can organize a discussion about things that are related to AI future, like robot learning, for example. So now, Jan, the floor is yours. We have an hour, let's say, minus 5 minutes now. So let's say 3/4 of an hour presentation, then about 10 minutes of discussion.
Sounds good. Well, thanks so much for the introduction. And I'm going to talk about robot learning. And before I start, allow me to start with a video. Now, this year is in fact such an old video, you won't believe it. It's from the 1960s, and it's a commercial from the first robot manufacturer ever, who directly promised us, well, we'll have robots in your home so soon that we can already demo how such a robot could perform in your kitchen. Now, you of course see how this robot looks, and it's quite clearly not well, what you would like to have in your kitchen. And by now, robots look much more beautiful. Our modern robot arms are not that clumsy anymore in terms of the size. We have computation, which is much, much cheaper and much more abundant back then. The supercomputers had computations back then that is less than what we have in every watch today. And so we've moved tremendously forward in terms of mechatronics and computation. Surprisingly, the way this was programmed back in the 1960s is exactly the way of how most of industrial robots today are being programmed. And the anachronism, if you just look at this couple where the woman stays as the stay-at-home mom who just drinks champagne in the kitchen while their husband goes off to work, it shows how anachronistic this is, right? We have accomplished so much as society, but in fact, we're nowhere close yet to have these robots. And that, of course, brings us to this really, really big question of why don't we have such robots? And it's actually quite devastating when you think of robotics as a discipline. And since today, you would really just have, well, if one of these objects was moved, the whole kitchen would actually not work. And precisely that way, the whole German car industry, for example, works. So let's ask the question the other way around. Not why don't we have such robots? Let's ask the question, where have robots been successful? And when you look at, well, the first thing which comes up to mind is, of course, car manufacturing. And in car manufacturing, there's one general rule: avoid every sensor you can avoid. And if it should be a sensor, ideally it's just one of touch, so it's just a switch, so that there is a minimal amount of sensing going on. And you really try to engineer sensing away, and you really try to engineer away all uncertainty. Anybody who's bought either a vacuum cleaner or a lawnmower robot knows basically that you have to reconfigure your environment. For the lawnmower, you probably have to put in a wire into your lawn, and for the vacuum cleaner, you typically have to, well, rearrange your furniture so that it doesn't get stuck. So with other words, when are robots successful? Whenever we adapt the task to the robot. And that is actually pretty bad scenario when you think about it. So this is really not what we're trying to promise in terms of AI. Now, I got started in robot learning when I was still an undergraduate student. And back then I started working at a very mighty classical robotics institute. the DLR Institute of Mechatronics and Robotics. And that was dominated back then by people who pursued the classical robotics worldview. So in other words, they were saying, we should do analytical robotics, since analytical robotics always suffices. And for analytical robotics scenario, you need 3 components. First, an accurate model. So in other words, a physics simulator. And yes, you can build very, very good physics simulators, and physical principles are a great prior. But unfortunately, they are quite frequently also quite devastatingly wrong, despite the usefulness. So for example, unmodelable friction and actuator dynamics, problems with the contact remain up to today in the moment where you have to use a physics simulator of any form. Then obviously the second component was, once you have a forward model, you can do planning with it. And whenever you can do planning, well, in this case, you have an exponential explosion of different situations. Replanning is, because it's so computationally expensive, hard, and you have a tremendous optimization bias in case your models are wrong, since, well, any incorrectness of the model will be exploited by the planning algorithm. And finally, the third silver bullet was, well, fast feedback control. And we all know feedback control is, of course, a fantastic error killer. We can eliminate many sources of error by something as simple as a PD controller. But unfortunately, it also made us build the wrong robots. It made us build robots which were stiff, power hungry, and have a very, very complex design, for especially given the duties it's typically has to perform. So that was the worldview 20 years ago when I was a university student, and it dominated literally everything. Now, whenever you have a pendulum, unfortunately, which is too far to one side, the next swing of the pendulum is too far to the other direction. And all of you guys are, well, totally engulfed, of course, in the new worldview, the deep learning worldview, where we have started to go to the complete opposite extreme, where we basically say, well, end-to-end deep learning is all we need in order to do robotics, since we have a highly flexible representation with suitable algorithms, and now we can learn everything. Unfortunately, that also means we can learn physically implausible solutions. And even worse, we can produce, with very small errors, we can very, very quickly already introduce gigantic optimization biases. And well, the solution we get comes with very, very few guarantees and very little insight, as it is typically black box. Now, the next big point, of course, was, well, we always have loads of data. And again, for deep learning, has made enormous success for computer vision, enormous success for natural language processing, where there's loads of data actually do exist. In robotics, on the other hand, well, robots live in real time. And we have a very bizarre situation because of that. Whenever you're learning a task, like let's say you're learning to hit a table tennis ball, in this case, you have very few episodes which you can actually collect because the robot lives in real time. At the same time, you of course have an unbelievably high number of useless observations of all the little redundant steps in between, because your camera sees at 60 Hertz, your robot generates its actions at a kilohertz. So we have very few episodes and a very fast state action stream. In real world, of course, means real damages. Nobody who hasn't broken his robot has ever actually properly worked with a robot. And well, whenever you come up with the first 2 bullet points, somebody in the audience will say, why don't we use physics simulators as data generators? But of course, that's back to square one. If you use a physics simulator as a data generator, well, you could just as well have just applied classical or analytical robotics. Why do you even need learning in this context? And then finally, well, there's a big question for loads of computation. And that brings up, well, how would you do online learning with loads of computation? How would you do relearning online how would you do store the energy if you had a mobile robot, or deal with communication problems in case you're losing connection to your learning system if it is off somewhere and not on. So, in other words, by swinging from one extreme to the next, we have also equally many, if not more, problems than before. And that, of course, brings us to the important point that true robot learning shouldn't be just like normal machine learning. It should also not be like just analytical robotics. It's just analytical robotics will not give us the robots we aim for, but just deep learning is very, very unlikely to succeed in robot learning as well. So how should robot learning differ? Well, it should really learn on the real system. That's a very, very essential component, since the real system doesn't lie about the data, the fragility of the solutions. It should be able to adapt online without replanning any form of complex search algorithm or anything like this. It should avoid the real-time bottleneck, but at the same time of like real-time bottleneck of a lot of data being generated, but at the same time be capable of coping with, well, relatively little episodic data, since 100 episodes can actually mean a lot of time. And then finally, it should be at least partially explainable, physically plausible, and cope with the optimization bias. And in the end, you do want to build the best bodies, not just the best bodies for feedback control. Obviously, I don't have the answers to all of these 8 questions, these 8 points, but I have had some really good lessons. And these I would like to address today, or at least some of them. And as a first step, I will tell you a little bit of how I think we should learn on real systems. And well, some of that view has already become mainstream in the last couple of years. Then I will talk about how we can learn comprehensible modular policies, how we can learn physically plausible deep models, and if we still have time, also a little bit on how we can build the best bodies and learn on real systems. Then an outlook and conclusion. So how should we learn on a real system from little data? Well, we should always try to start with data we actually have. So from my perspective, that means whenever we can, we should actually get our policy by imitation learning. Now, imitation learning, very classically, actually has as an objective that you should do similarity. And how better to measure similarity as by saying that we want to minimize the Kullback-Leibler divergence between the policy, so the distribution of our actions given the state, denoted by pi here, the state distribution, which is dependent on the policy pi, so that's why it's denoted as mu pi, which would be the new state action distribution. And we try to minimize the distance of that to the observed state action distribution denoted by Q. And that idea turned out to, well, generalize everything up to the earliest approaches to imitation learning, called model-free behavioral cloning, which goes way back to Michie and Chambers, who are among the absolute pioneers of AI, or Claude Sammet, who was the first to demonstrate that that model-free behavioral cloning can actually learn such complex things as flying a plane. Now, that of course throws away all the physics, which you could of course bring in as constraints in this optimization problem. And surprisingly, that's actually relatively recent that anybody ever brought this up. In fact, the first papers I know about who brought this into the problem are the work of Peter Englert or the work of Abdeslam Boularias, who both are former collaborators. The dual to this problem, if you reformulate everything in terms of Lagrangian multipliers, it turns out the Lagrangian multiplier functions in fact adjust the so-called value function, and well, you suddenly can derive quite a few of the inverse reinforcement learning algorithms, for example, from maximum entropy RL, right by forming the dual of this problem. However, this dual is also much harder than the original primal if you don't bring in further knowledge. However, if you bring in a minimal amount of physics knowledge, like for example, that you have second order dynamical systems, and you try to minimize the amount of physics knowledge you throw into this problem, you suddenly get both a formulation of policies, and you get a relatively fast mechanism for learning it. And well, this we call the motor primitive approach. And I should highlight one more time, the primal here, so the original problem is actually easier than the dual problem of inverse reinforcement learning. And we used this kind of an approach relatively early on. So this year was a task where actually my former control engineering student first failed when he tried to do it with analytical robotics. It's a ball and a string task. And for imitation learning, it actually worked out of the box. So you will see in a moment that you'll see in a moment how the robot reproducing this movement. So we have 4 cameras looking at the ball, and otherwise it's based on the joint encoders. And you can learn out of the box really nice rhythmic behavior. Yeah. Similarly, with such motor primitives, if you bring in more perception information, you can actually learn perception. You can learn behavior to new incoming balls. And well, after from very few demonstrations, you can actually already learn how to do basic table tennis strikes. Obviously, only strikes which are in the same family of movement, and to successfully return balls off the board. Now, imitation learning is obviously rather easy task and a rather successful way of obtaining motor policies. But as we all know, typically you don't get served the perfect behavior on a silver platter, but instead you need a lot of painful self-improvement. And for that, you're in the domain of reinforcement learning. And in reinforcement learning, well, you typically try to maximize the returns, where this reward function in there, denoted by RSA, is actually unknown. And what is quite bad, of course, is that even when you bring in, now again, assumptions on the policy and so on, you actually have no notion of data in the optimization problem you have in here. Of course, for a known reward function, in a known system, you could solve it, for example, by using linear programming. But, well, if you use, or similarly, you could again create the dual of the problem, or more efficiently than linear programming, you could solve it by using Bellman's principle of optimality. But this assumes a known reward function and a perfectly known system, and even then it's a rather hard problem. And what is quite bad, again, the primal is much harder than the dual. So the primal is actually this RL by linear programming. So these kind of problems actually tend to have a rather bad problem, that they have no natural notion of data. That's one of the reasons why, of course, in simulated environments and so on, you can make them work, but you can rerun things sufficiently many times, use Monte Carlo rollouts, so that you sample everything sufficiently much so you're represented by samples. But there is no easy way of doing self-improvement. However, if you do take just the 2 main steps from the RL problem and you add the objective from behavioral cloning as either a regularization term or as a further constraint on policy similarity, you can very, very quickly bring in some notion of data. And well, we figured this out actually quite a while ago, so more than 15 years ago. And it turned out to be hitting the nail really on top, since this has basically been underlying nearly all of the recent successes in both in our algorithms as well as in many others, since, well, depending on your choice of Q, so the data distribution of your original data, if you have any form of assumption on there, you can either get an analytical, frequently can get an analytical solution for the policy. You get very well convex optimization problems if you're linear in your features. You get all the different entropy regularization approaches. And you can, by linearization, you can obtain natural policy gradients. You can obtain TRPO. They're all just approximations to this particular problem. So this is actually rather cool that in the end, bringing the insights from RL and combining them with a slowness of the similarity measures from imitation learning, you actually get a whole family of approaches and lay the foundations for a lot of success in robot learning. The first time we actually used this was in this scenario where we have ball in the cup scenario. We first do a quick imitation. Now the robot doesn't have any hand-eye coordination after just one trial, and it also is has problems with its 2 kilogram wrist to reproduce the high accelerations of the human. And well, but you see a trial by trial improvement here. And already after 40-something trials, the ball goes occasionally into the cup, but in many cases just bumps off the rim, as you've seen here. And it becomes perfect after about 90 trials. And in fact, after 90 trials, you can let it run for days and days and it won't make a single mistake. So it really gets to perfection. We, of course, ask ourselves the question of, well, many questions here later. So one was, how good are humans? Turns out that, well, obviously highly biased samples, so relatives of PhD students, that kids of the age of 6 to 8 don't manage to learn this task properly at all. Kids at the age of 12 manage to learn it within 30-something trials, so they're slightly better than this algorithm. And grown-ups learned to do it within 3-4 trials. So it seems to be only me who took 3 months to learn this behavior. However, for the kids also we used chocolate as rewards, and some of the kids actually cheated. Now we've been pursuing this kind of a task since then for a very long time. And now here we were completely model free. So we only used only model inside was the one that we were working with physical systems, and therefore needed second order policies. If you're willing to bring in more physical knowledge, you can actually bring the number of trials down to 7 or 8 trials. If on the other hand, you can bring in more informative reward functions, then again you can bring also the learning speed down to 7 or 8 trials. So we can get into the ballpark of a grown-up. And that's pretty, yeah, I find it pretty impressive. Now, I hope to have made the case that we can learn from little data. We don't always need the billions of data points required by deep learning. Now, the next obvious question is, well, if you learn a policy, you would like to have components which you can understand, which are comprehensible, which you can reuse, so they got to be modular. And well, how can we learn such a comprehensible modular policy? So for that, we have to take this black box of the policy and turn it into a gray box. And well, we ideally want to have in there primitive behaviors. We want to reuse as much physics knowledge for execution as we can. And we would like to adapt the task based on grander context by supervising. And that gives us then, of course, a way of composing policies by, well, selection, superposition, and sequencing. And let's focus on the first of these two. And we would like to initialize this. And here, my former PhD student, Rudy Ludikov, really proposed a wonderful approach where he learned both the supervisor model and the primitives at the same time by modeling in the trajectory distribution resulting from the observed trajectories and then running an EM algorithm on trying to get first over segmenting so that you get way too many symbols, and then eliminating all the symbols which primitives are equal to symbols in this case until convergence. And well, he applied it both for learning different manipulation tasks as well as for well, basic games of table tennis, where he could find the most important primitives of table tennis. Now that gives us modular policies. And in fact, modular policies have been driving us for a very long time. And in the easiest case, the modular policy just means we need a gating network which decides which primitives to use. Here denoted by O is for O stands for options, and where then the actions are being generated by the primitives themselves. And they could be actually, well, they can be generated by multiple primitive policies and then recombined based on the gating network. Somewhat similar to a mixture of experts. Now, what does it do to our program from before? Well, the first thing we need to do, we need to introduce the options. Now that's a relatively naive extension. So all we need to do, plug in one more variable into all the different local policies so we can write them then together, the gating network and the actual policy. And we need to sum then also, of course, over the options. And surprisingly, or not so surprisingly, this actually works as you would expect it. So you can actually get good behavior here. The system can even predict whether to take forehands or backhands. It takes the opponent into account and well, learns its game of table tennis. But at the same time, you will directly see that there are certain problems. So for example, if you give the system a scenario where the system has to deal with two competing primitives which are equally good for the which could be equally good for the same problem. And well, if you let it run and learn, the two primitives will actually not specialize on two separate solutions, and therefore actually will always stay relatively poor. In table tennis, this did not occur for the simple reason that the different options were typically too mutually exclusive for this problem to become relevant. However, if you introduce in tetherball, for example, where you have a hole in your state space, this occurred in the state action space, occurred all the time. And so this problem became quite predominant. But we figured out an easy way for getting out of this. And this was to force the primitives to just have limited responsibility. And so, well, what happens then? First thing which happens is that your primitives specialize by well, having just limited entropy in the gating network, and so you learn in the end two highly specialized primitives. And even nicer, it actually gives you the possibility of getting a good performance, so much better performance than the naive approach or a monolithic approach with some form of a monolithic representations like a deep neural network. And at the same time, you get something else which is nice. You get a fast reduction in the number of primitives, which by a principled approach. Now, the naive approach, you can also eliminate primitives. Yes, but it's not such a principled approach. And while this higher-ups approach gives us a really good way of removing primitives altogether in a very principled way. And we have applied this in a ton of problems, like stacking a tower of objects as high as possible, like using a pepper mill, like moving when cutting an eggplant in a bimanual manipulation task. And yeah, all of these cases, learning both the gating network as well as the actual policy by behavior reinforcement learning was highly successful. So I hope to have made the case that we now know how to learn both context and primitives. Now the next big question, of course, is how can we improve our execution? And well, for improving execution of primitives, you want to generalize your physical knowledge across tasks. Now, as you know, for us humans, we have a hard time actually generalizing physical knowledge. So if you're a very good golfer, this doesn't tell a lot about you doing hockey swings. Or if you're very good at playing hockey, your golf does actually not really improve that much because of it. However, if you're generically good at sports, well, that typically helps also between sports, but it's not because of your skill so much as of your physics knowledge of your body. And in this case, implemented both at the biomechanical level as well as, for example, in the cerebellum. And it typically isn't just for the direct task. And that brings us to the big question. Well, how can we actually, well, generalize physical knowledge? And that also means we have to learn physically plausible models. And well, this is, of course, a huge opportunity for deep learning as well. And well, models are, of course, super important for execution. You want to learn inverse models for control. You want to learn energy models for underactuated control. You may need to learn a forward model for prediction or for filling in missing information about the state. So quite clearly, you would like to have models. And that again makes us feel like, oh God, oh no, we are back to square one, right? We're back to the scenario where we are trying to get to an analytical robotics worldview, but just now with a verse representation. And obviously that is the first right way of feeling about it, since the gut feeling should be, well, you can of course do model engineering, which is one of the most classical approaches. So you try to take your robot apart, you measure center of gravity, mass, inertia, and so on. And you can actually compute all the different kinds of models there are. Then, of course, you could do system identification, and you're lucky. Physics is actually linear in its parameters. So you have a somewhat well-defined optimization problem with only, well, one big bottleneck, that for physical consistency, it becomes a non-convex optimization problem. So it's not so trivial, as just linear regression. You have to actually always project back onto the constraints. And then you could, of course, do black box model learning, which doesn't allow you to learn, where you use, for example, a deep neural network to blindly learn a physics model. And in this case, you, of course, could only learn a forward or inverse model from your data. Now, each of these has a bad taste, right? And model engineering, you never want to take a robot apart. The system identification, you have to excite the system sufficiently so that you actually can solve this non-convex version of this linear regression with non-convex constraints. Or you have to, when you're learning a deep model, you may learn something which is completely physically implausible, and which doesn't give you an energy model, which also means you don't know how to solve underactuated tasks. Now, my PhD student, Michael Luther, who just 3 weeks or 4 weeks ago joined Boston Dynamics after graduating with his PhD, he after leaving my group and graduating from this PhD in April, he proposed the deep Lagrangian networks, where he creates a model makes sure that his deep neural network can only learn a physically plausible modular representation. So he puts in a really useful physics prior, and even figured out that you can learn all the 3 kinds of models with one deep network. And by bringing in just sufficiently much of an inductive physics bias, and so either the ordinary forward model, inverse model, or an energy model, you get each of these by just bringing in, well, by just choosing the right kind of a neural network structure. And you can even use is for each of these terms directly the right kind of right kind of an error function, which are obvious for inverse models, which are obvious for forward models, and somewhat surprising thing for energy models, where we never have explicitly energy, but we do have the conservation of energy principle. And well, these 3 losses you could minimize even at the same time, and therefore get one model to give you the output for all 3. And you can then nicely look at these models and understand them, which is super important when you want to do control with the model. And well, you get for in this case here quickly a 2 degrees of freedom robot arm. You get a near perfect torque prediction, and you can even isolate the different terms and look at the inertia term, the Coriolis and centrifugal forces, and gravity. And you see the prediction of each of these is nearly perfect, like already from very, very little data. So this next question, of course, was, well, it's apply this in energy control, and you choose a Furuta pendulum as the test case. So Furuta pendulum is basically like card pull, only a little bit harder because the base turns, it is not linear. And the analytic model, not so surprisingly, is very, very well tuned, and directly manages to get to the solution. And system identification actually fails here. And the reason for this is that the eigenfrequencies of that system are actually very fast, and they make it nearly impossible to use the sampling frequency of the system makes the system identification, the online and real-time system identification really hard. That's one of the reasons. The second reason is that the system never manages to explore enough to get a really good physics model, despite that it has all the physics basis functions. While DeLaN, due to the better generalization properties here, manages to learn the energy model right away, and then also uses it to do successful energy control to stabilize the pendulum at the top. So that was a nice proof of concept, and it turns out that you can also apply it for classical control. So here you see our Barrett WAM robot, and he manages a higher performance at accurate trajectory following at lower gains than the manufacturer. So that is a pretty impressive way of using the combination of deep learning and physical insight in order to really obtain good solutions for execution and for control. Now, the last question, I'm glad to see I still have time. The last question is very close to my heart as well. I grew up in, as I've told you before, in a lab where people were building robots by classical principles. They really tried to push the envelope at the robots they could build, right? I mean, many of you have been using Pandas or EVAs. They've been very thankful for these robots. They actually all came out of the DLR Institute of Robotics and Mechatronics, makes by their technology, and only because these guys pushed the envelope of classical robotics so much. But at the same time, you also see how much we have been stuck, right? We still have gearboxes is in there. They're still built to be modelable and controllable. And maybe it is time to change the dogma here. And the dogma should really be, we should try to build the best bodies, and not the best bodies for control, but really the best bodies for the task. And that also means the best body for learning the task. And well, when you look at humans, we have amazing bodies, right? Whether you look at this girl playing piano, whether you look at these table tennis players, then there's one thing. There's one thing you should really, really notice, and that is that they do amazing accelerations. And if they hit something, they don't hurt themselves. And at the same time, they're super inaccurate. So they reach very high accelerations, and they have, for very short amounts of time, very, very high velocities. And they learn on them without breaking. So you could make the claim that our high human performance is actually only due to the fact that we have built bodies which are optimal for learning, since the variability we have in our movement is great for motor learning, is really terrible for motor execution, and which well, are really built to do well human motor learning. And similarly, to reach human performance, robot learning also needs well human-like bodies, which can try high acceleration tasks and learn without breaking. Now, I got really interested in that already somewhat 15 years ago, and I built the first robot, and then the whole that whole project slept for a couple of years, and then I found finally a PhD student who Peter Büchler, who was actually willing to build such a robot. But again, and to do it right, got all the little knickknacks and problems out of the system, and yeah, he did a really good job. So he built a muscle-based system with extremely lightweight mechanical components. So this arm actually weighs 700 grams, but the muscles are all in the body, just like for us humans, where our arm is, well, it's actually to our arm. A human arm is closer to a little bit less than 2 kilograms, but actually most important muscles are all sitting in the base for us humans, and for very, very good reason. And well, he built a similar system, and then we did something pretty amazing with that system, since we just initialized the policy initially randomly. So we just gave it motor babbling. We just made sure it would move somehow. And of course, you don't want to lift the ball up all the time, but you can only do learning on the system because there is simply no good simulator for these mechanics. In fact, the simulator is so, all mechanical models obtained by classical solutions are so bad that there was a very famous mechanical engineer who visited us, said that this is maybe a computer scientist's fantasy, but it's a control engineer's nightmare. And well, we actually managed to do then learning against the simulated ball. So the ball is simulated, but the ball racket ball racket contact is simulated, but the robot only moves in the real world, and therefore, well, its real dynamics are being excited. And then, well, after leaving the room, sleeping over the night, the next morning, you actually have a behavior, and this behavior reliably returns, without having done any imitation learning before, reliably returns the ball over the net, and well, over the net in simulation. Then, of course, the next big question is, how well does it do on the? How well does it do on a real system? Well, here you see the performance, the different forehands on the real system, and you see that it actually manages, after another 30 minutes of training, to really hit real balls quite well, and in a way we haven't had it in previous systems. So I hope this gave you a little bit of a glimpse of the fun things we do, but I would really like to come back now to, well, the conclusion and the bigger picture. And so what should you have learned? Well, you should really have learned, if you should try to learn on the real system. That means, though, you have to consider 3 different things. Well, you either have to start with an imitation, just to bootstrap you really fast to good behavior, and then do maybe reinforcement learning. You should try to do, well, safe model learning methods if you want to do model-based RL. So this is still got to be an important part in the future. You should try to build bodies for learning from scratch, since in the end, for us humans, it's quite deciding that we have such a good body, and we would not be able to survive a day as a classically built robot. Then, well, I strongly recommend to use the right policy representation, such as a perception modulated movement primitives, whether that's DMPs, ProMPs, these are neural motor primitives or something else. We should try to avoid the real-time bottleneck. So we need to build on modularity in well-chosen parameterized policies, and which also enables us to cope much better with a little episodic data problem. Now, I didn't talk about this, but I strongly recommend reading Ludikov 2019 on how we can learn at least partially explainable solutions. And well, if you want to do physically plausible neural networks, start reading Michael Luther's work on DeLaN. And yeah, there are many ways of coping with the simulation optimization bias, but the work of Fabio Muratore on SPOTA, for example, is very impressive in this context. And finally, you should try to build the best bodies, not the best bodies for feedback control. That means small moving masses, ideally an antagonistic variable stiffness actuation, and a lot of robot learning. So robot learning for me stands at the center between robot engineering, machine learning, and, well, trying to understand why we humans, who have in the end only one real advantage on the motor side over robots, that's that we have such high accelerations and have bodies which are less likely to break, why we are so good at doing movements. And these disciplines, of course, thanks to robot learning, are really an interplay in our group. And we do obviously much more robot learning, whether it's more table tennis, whether it's automating stability proofs, whether it's new ways of doing reinforcement learning or learning of tactile skills. We also do a lot more on machine learning for control and imitation and abstract strategies and many other problems. And finally, we're super interested in figuring out why humans are so good and how we can transfer these insights. And yeah, let me stop here and say thank you for your attention and hope you have lots of questions.
Thank you very much, Jan, for your excellent talk. And the topic is very interesting and your presentation was very inspiring. Are there questions, please? Please just go ahead and voice your question, Rhea.
Oh, hey guys, everyone. I just want to find out, you mentioned something about avoiding real-time bottleneck. Can you please just elaborate on it? What do you mean by real-time bottleneck?
Okay, so in real time, we have to learn. If you want to learn in real time, we have to sometimes learn as fast as up to the next couple of time steps. So if you want to learn, for example, if you want to learn an inverse dynamics model online, you need to, and you change the dynamics of the robot by, I don't know, adding a weight, cutting a cable drive, whatever you like. You have to sometimes learn as fast as relearn as fast as in very few milliseconds. So you're always on a budget of how fast you have to learn. At the same time, you get a stream of data. So most of the time, nothing interesting happens in this data. Because you get data at 500 hertz for the Barrett WAM, which you see in this picture, or you get them at a kilohertz if you have an EVA, and you need to make sense of this data at a rapid pace, and there is sometimes very, very little in this data. And that's and the data never stops. So at some point you need to start forgetting data as well. Since if the dynamics changes, well, and how do you decide that the dynamics of your system changes, that your task changes, and how to cope with that? So that's that's basically the problem with this endless stream of data. But the signals or the completed tasks are in the end very few. So the number of episodes you have is always limited. And this is why I always highlight that we are in this crazy scenario where we have a lot of data and most of it is irrelevant. We have so few episodes that we never get to big data in the end. I hope that made it more clear.
Oh yeah, no, definitely. I do have a follow-up though. Just one last question. Yeah. But if already your model has learned, during test phase, how is like a real-time bottleneck an issue? Because your model has already learned how to deal with the dynamics.
Your model is learned. What do you mean by learned? You mean learned or trained?
Yeah,
or?
learned. Yeah, learned. Yeah. So if your model already has learned, maybe in some arbitrary environment, and now you're putting it in real case scenario, is the real time still an issue?
So if your model is already trained, it's and you never want to retrain it, so you don't want to update it again, then actually these days it's not so much of a problem unless that network is so big that you which it would never be in robotics, but that's a different story, that you couldn't execute it in real time. But I mean, then the big question just is, why do we need learning in the first place if we don't want to continue to adapt? And could we all, if we can just freeze the model, this is perfect. But most of the times you do learning because there are things which we can't foresee. And when you think about it, when we as humans, we relearn our models all the time, right? Even the models of your own body, because the wear and tear of your body is quite substantial. If you get in a new car, you relearn the models within no time. And this idea of, well, why don't we have a fixed model ahead of things? Well, it would solve, of course, everything. If we had the perfect physics model of all problems in the universe, well, we could, of course, predict everything and control everything. But in practice, well, we always will have to do some relearning again.
All right, thanks, appreciate it.
Another question, please. Well, if there are no more questions, then Jan, I would like to thank you very much for your very interesting talk. We work here on reinforcement learning for drone control so that it follows targets and does cinematography in a particular way. So if any of your students wants to cooperate with us on these projects, then we can discuss it offline, of course. Thank you very much again.
Thank you.
And